Recording has started.
Alright, welcome to today's Module 14, Routing Concepts. And what we'll be going through today is how routers determine paths, how they forward packets. We'll do the basic configuration review because it's been a while since we did a full and basic router. We'll look at the routing table that the router uses, and we'll look at static and dynamic routing concepts. So we won't actually be going through protocols per se in this course. That'll be in ENSA, which is the third section, which has the security and routing and automation in it. So that's in the next course, which we'll do as part of the diploma. So basically the primary function of a router is to pick up a packet from one interface, work out where it's going, which it uses the destination IP address to do that, and then to do a forwarding decision. In other words, what interface do I place this packet on for it to continue its journey to its final destination? So that picking up of the routing packet and making that decision is known as routing. So basically all it's doing is taking traffic from one interface and dropping it on another. Now there's many items that we can influence to make that happen, but we'll, as I said, that'll come up more in the next course than this couple of modules that we've got left for this course. So how does it determine which interface to drop this incoming packet on? Well, it has a reference table called a routing table, and this has all of its known networks listed and how to get there. So if they're directly connected interfaces, in other words, it's a cable plugged into the router. That's one way of knowing of a network. The other way is for a network to be manually added by the administrator, which is known as a static route. And how we do this is basically type in the network and the subnet mask and say you are connected to this network via the next device. And the other way of learning about networks is using dynamic routing protocols, which the routers share their routing tables with each other, basically. There's more to it than that, but we'll get into that when we explore the individual elements. So the best path is the one that matches the most. So when we have similar routes in the routing table, we try to match the most bits as possible. So if the network address is 24 bits long, it's best if we can match 24 bits. But if we can only match 20 bits, for example, it's still known as the best path because it's the matching of the most bits as possible up to the prefix length. Okay, so that we need to match the destination IP address in the packet with the reference networks in the routing table. So we match from the left bit towards the right, and we want to have as many of those match as possible before we select the path. As you are aware, we've spent quite a few periods looking at creating subnetworks. So we have a parent, and then we break it up into smaller networks, which we call child networks. And what we do with breaking up the networks into smaller parts is we create a series of networks that are more in the network portion than the original network. So we want to match as many of those bits as possible to give it the most accurate forwarding decision as possible. Now, it doesn't matter whether we're talking about IPv4 or IPv6, it's the same concept. But the examples we'll go through are for IPv4 because it's easiest. We're only dealing with 32 bits, not 128. So it's much easier for us to go through examples using IPv4. But it's exactly the same process we use for IPv6. Okay, we still match these binary digits and we try to match them as many as possible. So in this example, we're trying to route to the IP address of 172.16.0.10. So it has the binary all laid out with us. Now what we have is 3 networks in our routing table, all part of the 172.16 network family. One's a /12, one's a /18, and one's a /26. So you can see that the 12 matches the 12 bits. And then if we look at the 18, it gets through and matches 18 bits. And then the /26, we match 26 bits. Now, that is the longest match against the entries in the routing table. So that's the best match for the address, and that's the one we'll make the forwarding decision based on. As I said, it's exactly the same in IPv6. We look for the longest match. Now, we have a destination. Now, with IPv6, it always sends the CIDR notation, the /48 in this case. So we have an address, and it tells us how many bits of that address are used in the network portion. So when we go to the routing table, we have 3 entries. One with a /40, one with a /48, and one with a /64. We can't match the /64 because that is longer than the network portion of the destination. So that disqualifies itself. The /40 is a positive match, but the second entry, the /48, is the longest match because it matches all 48 bits of the network portion of the address. So that's a precise match, network for network. So that's the one it will use. If you try to match any more than the 48 bits, you're actually looking at the host portion. That is not used in routing determination. Only the network portion of an address is used to determine the path for that packet. Because routers only forward to networks. They don't care about the host portion. That is why we do a ANDing function to dispose of the host portion out of the address so that we can only make decisions on the network portions. Remember, routers connect networks, not individual hosts. Now, how we build up the routing table. As we activate an interface with a valid IP address, they become a directly connected network. So that's one way of adding a network. Then we add our remote networks via entering a manually configured, i.e. a static route, or via routing protocols which dynamically share their known networks with each other. Lastly, we've got a default route, which is a static route, but it's a special one. This is where we use a quad 0 with a no match bit. So we're not actually matching anything, it's a wildcard. So what this does is it says, if you do not have a specific match elsewhere in the routing table, you will always match the default route, and I'll forward you on to another device to see if they can forward you to a specific location. Now, default route is also known as a gateway of last resort. So if you actually look at the routing table, that's what it comes up as, gateway of last resort. So here's a nice little table that looks at how to pull it all apart. So the packet arrives, we get rid of the frame, passes it up into the routing function, and looks at the IP header to look at the destination IP address. It then uses the destination network after doing the ANDing function against that address to try to match an address in the routing table. If it finds a match, it forwards that packet to the outbound interface. Now, it then re-encapsulates that packet with a new frame header before placing it on the outbound interface. Now, there's two solutions to the outbound. If it's a directly connected network, it's forwarding it to the end device, a host. If it is not a directly connected network, it's forwarding it to the next hop or the next router along the path to its final destination. If it doesn't have a match in the routing table and it doesn't have a default route configured, the packet is dropped. It's discarded, put in the bin. So if it's forwarding on a directly connected network, as part of that process, it'll do an ARP resolution. So it'll send out an ARP request going, I need to send something to this destination IP address. Please provide me with the MAC address. Then it'll encapsulate it with the correct layer 2 header for the MAC address of that destination, and then put it on that interface and shuttle it off to its final destination. Now, as you know, depending on the media type, depends on the type of frame, but it's still Ethernet, so it still has the same type of format. When we do a next hop solution, we do the same thing, but the IP address stays the same as the original packet. All right? We do not change the destination IP address during its path to its destination. Remember that. We will do an ARP request again, but this time we're looking for the MAC address of the next router to forward it closer to its destination. Remember, the MAC address determines what device is going to pick up the frame. When there is no match, as I said, no destination possible, then there's nowhere for that packet to be forwarded to, so it's discarded. We need to forward it based on the IP addresses. How we get there will vary depending on how we're connected to other devices. So one of the secondary functions of routers is the ability to change media types in transit. So we can come off our standard Ethernet, then get put on a point-to-point serial link between two routers going across the internet. Alright, could be a frame relay link, it can be all sorts of different types of connections, and this is where our framing comes into play. Remember way back when we went through the OSI models, and the function of layer 2 was to ensure that the next device could pick up the frame. And that framing was dependent on the media type. Now, over the years, the mechanisms we use to forward packets has changed. Excuse me. So, as we develop technology, the process that we use to make this forwarding decision became faster. So the mechanisms was process switching, fast switching, and Cisco's has an express forwarding mechanism as well. Other vendors might have their own version of express forwarding, but let's have a look. So with process switching, every time a packet arrives, it needs to come via the entry interface, lift up from the data plane in the control plane where the routing function occurs. It determines the path and is then placed back down into the data plane and exits the next interface. This is done for every packet, so it does this calculation for every single packet that arrives, regardless of whether it's for exactly the same destination or not. It treats each packet as a brand new packet. Now, fast forwarding or fast switching is a mechanism where it goes, I'll only calculate this for the very first packet. So the first packet comes in, it gets passed up in the control plane and determines its exit interface. It then adds an entry into the fast forward cache saying if it's coming from this source going to this destination, this is the exit interface. Don't need to go through the whole process again. So it basically reuses that calculation by using this forwarding cache. So only the first packet goes through the full calculation as process forwarded, and the subsequent packets just get forwarded via the cache, which has greatly reduced the CPU requirements on the device and increased the efficiency and speed that packets are processed. The next version is Cisco Express Forwarding, which is basically all of Cisco's latest iOS's preferred method. So with Cisco Express Forwarding, a forward information base is created with all the adjacency tables. So basically what it's doing is, okay, I know all of my networks, so all the possible forwarding decisions are, and it calculates them pre-packet arrival. So it has a combination of what's the potential source networks that I know being forwarded to all my potential destination networks, and I'm just going to create an express forwarding base before any packets arrive. So it's created this express forwarding table, pre-built it, pre-populated it. So it's done all of this pre-calculation before traffic even arrives at the router. And because it's running in a cache, it's very fast and it adds very little delay. So let's review a basic network configuration. And here's one of the many table topology that we had examples of over the period. And we're going to be looking at router 1. So router 1 has 3 directly connected networks, and it has to forward everything to router 2 to connect to router 2's known networks and get out to the internet. So let's start off with the basics. Quick review. Enable to get from the user mode to privilege mode. Config T to get in the global config. Then we go through configure the host name, put in our secret password, which is prompted for when we change modes. Then we configure our lines, our line console with our password and the login, and the V2Y lines with a password and login, and we specify how our remote connection is going to be handled. Preference, SSH, and then telnet. Because our passwords are in plain text, we want to give them a little bit of protection with the service password encryption, followed by our warning banner message of the day, basically warning that unauthorized access is prohibited. And then we go in and configure our interfaces. Now, if we are using IPv6, it needs to be enabled, as only IPv4 is enabled by default. So we need to include IPv6 unicast routing. And then we can go to our interfaces, put our descriptions in, our IPv4 address, and then our IPv6 address. Now, in this example, we are manually configuring our link local addresses rather than having them dynamically configured, as link local addresses we don't have to manually configure. They will self-generate. But by putting in manually, we can shorten the address if we desire. Then we do a copy run start to back up the config file from RAM to NVRAM, so that if the device loses power, we'll restart with that. All the interfaces configured with basic security, so we prompt for passwords, and we have a host name configured so it can identify which device this is. And just a brief run through the commands again. So show IP interface brief to give you a summary of the configured interfaces. Show running config, and then we have various sub sections where we can actually go in and specify an interface. And then using the pipe symbol, we can do sections or begins. There's quite a few options with the show running config command. Show interfaces will give us a list of all interfaces on the device and show us explicitly the layer 2 information for that interface. Show IP interface gives us layer 3 information, concentrating on the IP protocol. Show IP route will show us our forwarding table, and ping can be used to confirm connectivity to another device. Now, replace IP with IPv6 for their version of the same command. As I said, with the show commands, we have the pipe options, section, include, exclude, and begin, so we can filter the output of the various show commands based on subsets. This is very useful, especially with the running config, as it can get quite large on the more complex devices. So, how do we know how our little network table was put together. So how can we tell whether it's directly connected, a static or dynamic routing network? So the source of this information is identified via a code. The most common codes that we'll look at are as follows. L identifies the assigned local interface address. So it's the link local address effectively. This only came about after IPv6. Before then, we only used the C, which identified the directly connected network. S identifies a static route. O is one of the dynamic routing protocols called OSPF. The asterisk is a candidate for default route. We can have more than one candidate, and out of the candidate routes, it then selects the gateway of last resort. So each router makes its forwarding decisions based on its own information in its routing table. If that route is not in its routing table, it doesn't exist as far as that device is concerned. One device's routing table does not necessarily need to or does match another device's routing table. There's all sorts of reasons why devices will end up with different entries in their routing tables, none of which we'll go into in this course because route filtering and other things like that can get messy and requires a bit of practice to get your head around. And as we don't, I'll just leave the filtering until the chapters that we get to, which is, as I said, in the ENSA course. Now, each path is determined from the routing table. Now, for the selection and determination, the information used to build the routing table can be received from many sources, and only the best path for that network will be placed into the routing table. So this is another reason why routing tables will change from one device to another. Okay. My phone is going nuts today. Okay, so how do you read the information in the routing table? So here we have a fairly standard line from a routing table. So the first one tells us how the route was learnt. In this case, was learnt via OSPF. Now I really shouldn't click. Next is the actual network, the destination network, followed by the subnet mask or prefix. So this tells us the destination network. Following that, we have a weighting. The administrative distance tells us how trustworthy this method of learning the route is. As we have many different ways of learning a destination, we need to know which one is more trusted than another. So the administrative distance tells us which one's more trusted. The lower the value, the more trusted the path. The number after the / is the metric. In other words, for a metric, it's the cost. What's the cost of me using this path? Okay, so if I had another path to the 10.0.40 network from OSPF, but its metric was 80, I have a cost of 50 and a cost of 80. Which one's more efficient? The one with the lowest metric. So when I have multiple paths to the same destination, learnt via the same way, I'll use the lowest cost to get there, or the more efficient. Following that, we have the next hop. This identifies the IP address of the next device that we need to forward packets to get it to its final destination. Following that is the time since this path was learnt. And then we'll have the interface to forward this packet on. So this is our outbound interface to get to that network. So we forward packets for the 10.0.40 network out of serial 011 to the next device at address 10.0.32. The same information can be found in the IPv6. As I said, the L is a relatively new one. The local connection came about when IPv6 came about with its link local addresses. So for an IPv4, our link local, our L network, is a /32 address. So the IP address that we configure on the interface is shown in the routing table with a /32. So we not only know what our connected network is, we know the IP address of our local interface, and that's shown in our routing table. This information was always known to the device. It's now just represented in the table. Next up is our static routes. As I said before, these are manually configured and they define the path to connect to a network. Now, on small networks, having static paths are efficient. We lose that as the size of the network increases, as every device within the network needs these paths manually configured in each router. Okay, so the default route can be created using a static route. Let's start. Alright. And we tend to use the default route where we've only got a single path going towards the gateway. So if we're what's basically considered a stub network, in other words, we only have one connection going upstream, it's very efficient for us just to do a static route saying all other networks are connected upstream via the next device. Command structure. This is a global command, so we do it from the global config, and the command is IP route. We then specify the network, the subnet mask, and the IP address of the next hop. With dynamic routing protocols, we set up the protocol on the device, and the protocol will talk to its corresponding partner on the neighbor, and once it has two-way communication with its neighbor, it basically shares its information and maintains that information by constantly checking with each other for updates. Our example is using IP OSPF. So we look at the output of a show IP route. What we're looking for is routes with O for OSPF, and in this example we have two going to 10.0.40 and 10.0.50, and they're connected via a serial interface. So the same information is displayed via the show IPv6 route for IPv6 networks. You can see there it'll give us the O, the network, the subnet mask, the administrative distance, the metric, the next hop address, and the exit interface. As I said, the best way to connect to unknown routes is by having a default route. This takes the burden of knowing all the other networks within the world. Okay, so a default route is quad 0, and this means no bits need to be matched, so therefore everything matches, and this will be used to forward any routes not previously matched. Remember, the routing table, we match as many bits as possible. So a default route means we're not matching any, so it's 0 match, but we don't discard the packet. We forward it on to somebody else, and it's their problem to sort out. It's past the buck time. So our structure of our routing table, you need to understand that it's basically the same structure as per the original IPv4. So it was built around classful addressing architecture, which we no longer use. Alright, we no longer use classful addressing. So we don't segregate our routes into classes A, B, and C. But our routing table will still break out the networks based on these architecture. So what it'll do is it'll come up with a parent based on the class address architecture, and then list its children or its subnets individually underneath that parent, which are known as child routes. These children will be indented so that they can be seen as belonging to the parent. So here we have the list, and you can see here that we have the parent 192.168.10/24, and it's saying it's variably subnetted. In other words, it's got subnets that are broken up underneath it. So these two are the children of this one. These are parents in themselves, so they'll be just straight there. 12.0 is variable. It's got entries for it. Now, because we have the C and the L, this is generating the parent and child. IPv6 does not have this feature because it was created recently and doesn't conform to the architecture of the original IPv4. Next up, we have administrative distances. As I said earlier, we need some way for the router to determine what way of learning about the path is the best. In other words, what one does the device trust over another? So do I trust what the administrator is telling me is configured, or do I trust what different protocols tell me? So which one's going to be more valid? Because each protocol has a different way of calculating the cost to the destination, the metric, and it would be like comparing apples and oranges. So the router needs to be able to filter based on a preference of how I learn paths. Directly connected is the most trusted way of learning about a network. Next is manually configured, the static routes. And then we go through the various protocols that can be used. As you can see, there's quite a few there with quite a differing range of administrative distances. So if I learn a path to the same network, one via RIP and one via OSPF, which one do I trust the more? I'll trust OSPF over RIP any day, because RIP only counts the hops to the destination. OSPF counts the links, how much bandwidth I have, what is the fastest path to get me to the destination, not what is the shortest in intervals. So to give you an example, RIP might come back saying, I can get you to the destination 2 hops, but those 2 hops are via a 64K link. Whereas OSPF might go, I can get you to the destination, but I'm going to take you via 4 links that are at 256K each, so you'll get there faster. So this is why this table was created. Static or dynamic? As I said, there's pluses and minuses for both choices. On very small networks where you're not going to have very many changes, static routes outweigh the choice very easily, because you don't have a high likelihood of having to change entries for those networks. Whereas if you had a more complex network, then you have a lot of time setting up all those static routes, and if something changes, those routes become invalid and you have to manually go around to every device changing those static routes. Very time consuming. Alright, so the most common reason we use static routes is setting up a default route to forward to our service providers. Then it's up to the service provider to know where all these other destinations are. So we don't need to learn all the individual routes from the outside world. When we want to get to a specific network in a specific network in a specific way, we can configure a static route for that. It's also very efficient to have static routes on stub networks. In other words, one way in, one way out. So the chances of the networks changing is very minimal. So rather than having this constant exchange of routing tables between routers, we can just configure static routes and cut back on the overhead. This is quite efficient, especially over the slower serial links that quite often occur with WANs. Dynamic routes are very easy administratively. We go in, configure them, and let the protocol do all the maintenance for us. So if a topology changes, the protocol will update all its neighbors saying something's changed, we need to have a recalculate the paths to try to get to the destination another way. These are very scalable because all what we've got to do is add our networks and the protocols will do the work for us. So here's a little comparison chart. So as you can see there, the complexity of configuration increases as the network size increases for static. And I'll let you read the rest of that table all by yourself. You don't need me reading the PowerPoint out to you word for word. Basically, it's a summary of what I've just went through. Protocols evolve over time as we get advances in technology. We get an evolution of protocols. So some of these kicked around: interior gateway protocols, external gateway protocols, RIP version 1. So these came about really early and they didn't really evolve for a number of years. Then we started having other departments and researchers start coming up with different ways of making those forwarding decisions, trying to make more efficient use of the networks as the popularity of networking and interconnected networks evolved, so did the need to make this process more efficient. So we basically had version 2s come around when we did an update to the way we did addressing. Then we did the next generation of protocols, or version 3 of the protocols, when IPv6 was introduced. So when we're looking at dynamic routing protocols, things change as technology and knowledge changes. The basic function of how it calculates the path comes in two forms. Distance vector, which basically says go in that direction and it's X amount of hops. Link state is protocols that go in that direction and all the links added together cost you X amount. And we can separate these protocols into interior and exterior. An interior protocol is our organization's protocol. It's the protocol we use within our organization, but we do not communicate with other organizations. So we don't share our routes with another organization. Exterior protocols are the ones that interconnect ISPs or the organization to organization. So the official term is autonomous system to autonomous system. Basically, a set of networks that are commonly administrative is known as an autonomous system. So all those networks interconnected together under the one administrative team is an autonomous system. When we connect that to another set of locally administrated networks with another organization, we need a common protocol to share information between those two organizations. It doesn't matter what interior gateway protocol we're using. Our exterior gateway works with its own pathing, its own method of determining the path, and generally speaking, border gateway protocols, which is BGP, is more stable because it takes longer for changes to impact its routing table. It's built to interconnect service providers with the minimum amount of updates between them. So, what is the purpose of dynamic protocols? Well, they're used to discover remote networks, maintain the routing table information with the latest information. It then determines which path to the destination is the best one, and then adds that best path into the routing table for the device to make its path determination on. It has mechanisms to keep that information current. So if a route times out, in other words, it can no longer be confirmed, it gets removed from the routing table. To do this, we have a series of structures to contain data. These are basically tables or databases that are kept in RAM that contain the various information about networks and how to get them. These tables are kept up to date with protocol messages being sent between its neighbours and exchanging information about the known networks. They are also used to maintain an accurate accounting of the information within the network. Then we have the various algorithms that the various protocols use to calculate the best path to the destination. It's the output of the algorithms that are entered into the device's routing table. And when we have multiple protocols or other sources of information for the same network, that the device uses the administrative distance to determine which of those sources of information it's going to use. As I said, the best path is the one that's entered in the routing table. So we need to understand that not everything is equal. So RIP uses a hop count, and for every router that it travels through, it adds one to that count. It can have a maximum of 15 hops to be a valid route. Open shortest path first, OSPF, uses a calculation based on the bandwidth of each link between the routers, and it's weighted. So the lower the speed, the higher the cost. An ERGRP uses a combination of bandwidth and delay in its calculation by default. It also has a maximum hop count that is allowed, but it's much higher than 15. Okay, it can be adjusted, but it's a couple of hundred. So we have different ways of getting to the same destination, and the device will determine which of those it will use. Now, if we have multiple paths costing the same from the same source, we will load balance between those paths. So if OSPF tells me there's two paths, I can go out serial 1 and serial 2, get to the same destination, and they both cost 50 to get there. I'm going to send even packets down the left, odd packets down the right, and balance it so I don't overload any networks. And this only works when the AD and metric values are exactly the same. Thus, equal cost load balancing. EIGRP supports unequal cost. So what I can do is put a variance in this protocol and say the best path costs me, say, 60. If I put a variance of 2 into its calculation, it'll accept paths up to 2 times that cost. So any paths that come up to a total cost of 120 will be valid and entered into the routing table, and it will share the load across those multiple paths, even though they're suboptimal. But it will send 2 packets down the 60 cost to every 1 down the 120. So, check to make sure if there's packet traces, probably will be. Definitely should be one for the basic device configuration and other activities. So, in summary, what did we go through in this chapter? So we looked at how a device, i.e. a router, determines what path to forward a packet. We looked at the fact that it uses the longest match of bits to select the best path. And then we looked at how networks get added to the routing function. So the fact that we have directly connected static and dynamic ways of adding paths into our tables. We then looked at the processes that packets can be forwarded. So process switching, fast switching, and express forwarding. We did a review of the basic show commands. We looked at how networks are displayed in the routing table using the format, and we went through how each section of the table displays a slightly different part of the picture, that being the route source, the destination network, the administrative distance, the metric next hop, how long ago the route was learnt, and the exit interface. We looked at the fact that we can statically enter networks, and we also looked at the fact that we can have a special static route called a default route that would match everything as a last resort, so that we do not discard all these routes out of hand. We had a look at the differences between IPv4 and IPv6, which is basically nada, okay? Other than the fact that the addressing information is different between the two protocols, because one's 32-bit and one's 128-bit, but the format's the same. That's the network. This is how it was launched. This is the cost to get there and how trustworthy the process is. Okay, so lastly, we talked about the differences in all the various protocols, the difference between interior and exterior gateway protocols, how they exchange information between themselves, and we had a brief discussion about autonomous systems and what they mean. We also talked about the fact that dynamic protocols are more easier on us as administrators as our networks become larger. They are automatic processes, so they require less and less work from us as administrators as our networks grow. Then had a very brief introduction in the distance and link states protocols and the differences, and the basic structure of how these protocols use different database tables to build a picture of the topology, and they then run their algorithms over that knowledge of the world to select the best paths to the destination, and then they put those best paths up to the device for consideration to be added to the routing table of the device. And we finished off looking at load balancing between multiple paths to the same destination and how that works. That brings us to the end of today's presentation, and I'll stop recording there because I know you all ask lots and lots of questions if you're still awake.